So, second page, still more ways to evaluate the limit using direct substitution. So again, if I take a look at this first one, it does tell us that we're going to rationalize, either the numerator or the denominator. But so back in pre-calc, when you would rationalize, the whole idea was to get the radical out of the denominator, right? You weren't allowed to have it there. So I have some good news for you. You have graduated the calculus, so if you get an answer with a radical in the denominator, you get to leave it. Okay? That is your prize. All right? So you do not have to rationalize. So if you get like 1 over the square root of 2, you can leave it. I mean, you can rationalize it if you want, but why? I mean, you don't have to. All right, so what's going to happen here is if I use direct substitution, okay, and I plug in 0, we end up with the square root of 2, because 2 plus 0 is 2, so it's the square root of 2 minus the square root of 2 over 0. So again, I mean, yes, you could do this just in your head, but this is still, again, what? Indeterminate. Indeterminate. We cannot determine a value. So what we have to do is we need to rationalize. So problems like these are actually designed so that whatever is causing your fraction, your rational function, to be undefined, excuse me, meaning a 0 in the denominator, it will cancel out if you perform the procedure correctly. There is a problem in the homework that if you multiply it out, it gets all this long, convoluted answer. Don't multiply it out, and then things will cancel out, and then it will work out nicely. So are we allowed to have zeros in the numerator of a fraction? Zeros in the numerator. Yes, of course. So 0 divided by 1, 0, right? But we're not allowed to have zeros in the denominator. So regardless of the fact that the square root of 2 minus the square root of 2 of 0 in the top, don't care. What really is making this more undefined and indeterminate is the fact that I have a 0 in the bottom. So what's getting in my way is the fact that if I have that x in the bottom and I have to use direct substitution, if I get rid of that, won't that help me? Okay, so what we're going to do is we're going to rationalize. And when we rationalize the numerator, that means basically you are putting the radical back in the denominator. So I've got the square root of 2 plus x minus the square root of 2. I'm just rewriting the original problem. Okay, and we're going to multiply by the conjugate of the numerator. So the conjugate of the numerator is the exact same numerator, except in this case the subtraction becomes addition, right? So we've got the square root of 2 plus x plus the square root of 2 over the same thing. So remember, we're not changing the value of the function, we're just changing what it looks like. Okay? All right, so in the numerator you have what's called a difference of squares. Example would be x plus 2x minus 2, x plus 5x minus 5. So remember, when you would multiply those out, the outer and the inner, when you FOIL, they go away, they cancel out. Do you guys know what I'm talking about? Yes? Okay. So that means when I multiply the top, can't I just multiply the first and the last? It makes my life a little bit easier, quicker. Okay, so what we have is the limit as x approaches 0. Okay, so what is the square root of 2 plus x times itself? 2 plus x, okay. Minus, what? 2. Divided by, do not multiply this out, because really what I want to happen is I want that x to go away. If you multiply it out, then I have more x's than what I want. So just write it as a product, x times your conjugate. Okay? So what happens in the numerator? You got 2 plus x minus 2. What happens? The 2's are gone, right? So I've got the limit as x approaches 0 of x over x times my conjugate. Okay? Now what can I do? Now my x's can go, right? I can get rid of that silly thing. What's in the numerator then? Ooh, I heard 0. JK, what is it?
1.
It's a 1. Oh my gosh. It does. It does. It's just terrible. Okay, so this is now what I want to try direct substitution on. Okay, so when I plug in 0, I'm left with 1 over the square root of 2 plus the square root of 2. What is that? square root of 2 plus the square root of 2. How many square roots of 2 do I have? So it's 2 square root of 2. Am I done? Remember, you have graduated to calculus. You do not have to rationalize. You're done. This is it. This is your answer. Okay? So provided we don't put that 0 in the numerator, okay, we're good. Questions? Everybody's all right? Okay, so let's take a look at this problem right here. Complex fractions. So this is when you have a fraction over a fraction, or just a fraction in the numerator and something in the denominator, or vice versa. Okay, if I were to plug in, let's just check. Plugging in, using direct substitution, I've got 1 over 1 minus 1. Okay, 0 on the top. Is that a big deal? We're allowed to have 0 in the numerator, that's fine. But then I have 1 over 1 minus 1. Okay, it's totally indeterminate, 0 over 0. So now we need to simplify the complex fraction. So how do I do that? Does anyone remember? It's a fast way, but you need to look for something in the top and in the bottom. Perfect. I need a common denominator from the top and the bottom. In this case, it's very simple. What is it? It's just x, right? Because this is currently sitting over 1, so the common denominator is x. This is sitting over 1, common denominator is x. So we're going to multiply by x over x. Now guys, remember, when you are multiplying by the common denominator, you are distributing this to everything that's here. Meaning, when I multiply x times 1 over x, what does it give me? X times 1 over x.
1x over x.
So x over x just becomes 1. The x's cancel out, right? And then you have x times x, which is x squared. Okay, so we have the limit as x approaches 1. You told me that when I distribute here, this becomes a 1 minus x squared over. What happens when I distribute here? Right here.
1 minus x.
It becomes 1 minus x. Okay. We have simplified the complex fraction. Jay, you good?
Yeah.
Okay. Are you sure?
Yeah. I understand now.
Okay. You had that deer in the headlights look. I was a
second,
little scared. Just for a second. That's all it takes is a second.
But then I figured out what I missed.
Okay. You blinked, right?
Yeah.
Yeah. Okay. Try direct substitution. What happens? 0 over 0. Okay, so I'm not done. I need to go another step. In this case, it's not just about simplifying the complex fraction. I need to take it another step. What can I do? Yeah, I can factor the numerator. The numerator is special. It's a difference of squares. So I have the limit as x approaches 1 of 1 minus x. That's a 1. Times 1 plus x over 1 minus x. So now these are gone. That was what was causing that 0 in the denominator, right? So you have the limit as x approaches 1 of 1 plus x. Okay, so now we simplify the complex fraction. We had to factor as well. Let's try direct substitution. What do we get? All right, we're good. We got an answer. Questions? Are you sure? Okay, so yes, ma'am.
So when we do the direct substitution, do we put the limit notation still?
Okay, so when I get to this point, I'm using direct substitution. Mm-hmm. So I'm just plugging in 1. So you drop it here. So you keep it, drop. Yep. Anything else? Okay, so up to this point, what we've done is direct substitution, especially if it's just a polynomial. And again, that's just a very general term. It could be x to the 85th power minus 1, and you're looking to evaluate when x is 2. Okay, you're going to need a calculator for 2 to the 85th because I don't know what that is off the top of my head, but you would plug it in. It's going to be this humongous number, and then you would just subtract 1. Okay, everybody good? Polynomial. You might have to factor. Always try direct substitution first. That's our ultimate goal because that's the quickest, easiest, and fastest way to evaluate a limit. Direct substitution. All right? So piecewise functions, we actually need to go back to what the definition of a limit is. So I'm going to review that right here. So the definition of a limit. I know there's not a space for it, but evaluating this problem is not that long. So here, if you're evaluating the limit, if the limit, let me move this up, as x approaches some given value a, let's say from the left of f of x, is equal to the limit as x approaches some value a from the right of f of x, and we're going to call that some value L, I don't know, a number, 5, 7, negative 0.75, whatever it is, then the limit as x approaches a overall of f of x is equal to L. Okay, this is really important. You need to make sure you remember this, because when you're dealing with a piecewise function, it's going to help you. Okay, so this is how we've been evaluating limits anyway. We evaluate the limit from the left, from the right. We see to make sure, especially graphically, if they're meeting up. Okay, so here I'm given a piecewise function. It says evaluate the limit as x approaches 3, given that f of x is x squared for any value greater than or equal to 3, or the linear function for any value less than 3. Okay, so anything up to 2.9 repeating, right? So what I need to see is, if I evaluate the limit as x approaches 3 from the right of f of x, okay? Let's do from the left. I'll stick with the definition. Sorry. Okay? Of f of x. Which function am I using? The top or the bottom? The bottom, because this is any value less than 3. So what that means is I'm going to evaluate the limit as x approaches 3 from the left using 6x minus 4. Okay. Remember what I said earlier? If you're evaluating a one-sided limit, don't try to plug in 2.999999. This is a non-calculator question. Just plug in 3 and see what happens. So here, when I plug in 3, 6 times 3 is 18, minus 4 is 14. So as I approach 3 from the left, so from your perspective like this, okay, my y value is up at 14. So I want to see if I evaluate from the right if the same thing is going to happen. So here, if I evaluate the limit as x approaches 3 from the right of f of x, that means I'm using x squared. What does that give me? Yeah, 9. Okay, so as I'm approaching from the left, I'm up here. As I'm approaching from the right, I'm down here. What's the problem? Yeah, it doesn't exist. So then you would write the limit as x approaches 3 of f of x does not exist. Now, I know you can do this in your head and look at it, but when I read your paper, when you're taking a quiz, or when you're taking, I can't read your mind. I don't know what you were thinking. You need to show me. This is your proof right here. This is your answer. Okay, so the expectation is that you don't have to write the definition, but you need to do this part. Okay? Questions? No? All right, let's take a look at f. Here again, we have a piecewise function, and we want to evaluate the limit as x approaches 2. This function actually has a point defined. Okay, but when I'm evaluating the limit, do I care when x equals 2? I really care about what's happening from the left and from the right. Okay, so here we're taking a look at the limit as x approaches 2 from the left of, which one am I using? I'm going to skip this part. Yep, I'm going to use the top, so 3x plus 1. So that means if I plug in 2, what do I get?
7.
Yep, 7. Okay, so let's evaluate the limit as x approaches 2 from the right. So what am I using? X squared plus 3. Okay, so when I plug in 2 squared is 4 plus 3, 7. Okay, so does the limit as x approaches 2 of this function exist? Where? Yep. So what this means is basically I have a graph like this. Here's 2. I'm up here at 7. Here's 8. So that means anything that is greater than 2 is going to be a quadratic, I don't know, like this. And anything less than is going to be linear. This point is an open circle. Because they're saying that at 2, this is what you have. That's basically what you've got. So the limit is what we're concerned about. You don't care about f of 2. Unless we're talking about continuity, which will come later. Okay, if you don't have a calculator, look on with the person that's next to you, but you do need to have a calculator. We're going to take a look at these two functions here. So in your calculator, you want to go into y equals, okay? And we're going to put this function in right here. So you want to go into alpha y equals and grab this numerator over denominator. And I want the absolute value. There's a couple different ways you can get this. For the newer calculators, if you go alpha window, it's the very first one. Okay, so absolute value. We're going to throw the x in there over x. So just hit zoom 6 and it'll give you a standard 10 by 10 window. Okay. So first of all, is there any place on this graph that the function is not going to be defined? You can't tell by the graph, but if I went into the table and went into the table, where is it? It's at 0. It's not. I mean, that should be obvious to you, though, right? If you put in absolute value of 0 is, well, 0, but 0 on the bottom. It's indeterminate. So what we have is a graph that looks like this. Up here at positive 1, this is an open circle, and the graph is going like this. And down here at negative 1, the graph is going like this. So if I'm not mistaken, and I put this function in, but I do x over the absolute value of x, I think I get the same graph, I think. Yeah, it's exactly the same. So what I was double checking is, it's this function, or even if you had a variation thereof that looked like this maybe, meaning the absolute value is in the bottom. It doesn't matter. This is what the graph is going to look like. So what's different about this function? Did anyone put this in already? It flips over, right? It reflects, right? Just like if you had a negative for the quadratic function, it was a reflection over the x-axis. It's the same idea. So that means this graph goes like this. Do you think the same thing would happen if the absolute value was in the top and the negative x was in the bottom? Yeah, there's the same variation. So the reason why I'm telling you this is these types of questions are typically asked as a non-calculator, so you kind of need to know the graph. It's just like knowing the parent functions of a line, or a parabola, or a cubic, right? You know what the parent function is. You can do the translations or the transformations. Same idea. Because in this next question that we have here, one-sided limits with absolute value, okay, these are very important, okay? You'd be asked this question without a calculator, okay? All right, so this right here is very similar to A or B. A, because the x is not negative. So what that means is the graph is going to look something like this. But this is a transformation. Think about the quadratics. Remember when you guys had something like this? Tell me the transformation. Right 2, up 4. So inside is opposite of what you see. Do you guys remember that? So when I take a look at this, tell me the transformation of this graph. Exactly. So that means this parent, everything's going to shift right 3. So if I were to sketch the graph, I've got 1, 2, 3, but there was no vertical shift, agree? Nothing up or down. So that means that my graph still looks like this. Does everybody see what I just did? Okay. So now if I ask you to evaluate the limit as x approaches 3 from the left, where's my y value? It's at -1. So the answer is -1. But this is not something intuitively you might know. This is something that you need to kind of commit to your memory. What does the graph look like? What does the parent look like? What happens when the x is negative? How does that work? Okay? Questions? You sure? Okay. What if we have a function that has a vertical asymptote? That means I have a rational function. It's not a polynomial. Okay? but I have a function like this that has a vertical asymptote. If this is a vertical asymptote and my graph is approaching, let's say this is at 5. My graph is approaching, what's going to happen? Is it just going to slam right into it? No, what's it going to do? It's either going to go up or down, right? So I need to figure out what is the end behavior of this function. So there's a couple different ways that you can actually do this problem. I actually like the way that I'm about to show you because you're going to have to do this anyway. Do you guys remember when you had the rational function inequalities, you had to do the critical numbers and you had to do the number line and find out where the function... Okay, so there's a couple things that I'm going to talk about here. You may or may not have heard this, so I just want to cover it a little bit. So the first thing that we want to look at when we have a function that has vertical asymptotes is where are the vertical asymptotes. In this case, there are 2, and they occur where? Plus or minus 2, right? If I were to factor this, my function looks like this. Agree? Okay, so we have vertical asymptotes where x is equal to plus or minus 2. Okay, critical numbers for a rational function, for those of us that have forgotten because it was all summer long and we did no math, come from the numerator and the denominator, meaning you set any part of your function with an x equal to 0 in the top, solve for x, and in the bottom. So that means my critical numbers that I'm going to throw in the number line are where x is equal to 0 from the numerator, positive 2 and negative 2. You guys remember that a little bit? Scotch. Okay, so I'm going to put a number line here. Okay, and the number line is just going to be split up given my critical numbers here, negative 2, 0, and 2. Is this kind of coming back to some of you? So then remember you would pick a number in the interval, plug it into the function, simplify it. Is it positive or negative? I'm going to show you another way to do that. Little trick. Okay, so if you recall, sometimes there are patterns to these. Okay, and sometimes you can't verify that, but there is actually a way to do it. Like typically this would go positive, negative, right? Or sometimes it would go positive, negative, positive, positive. Okay, but it's based on what's called the multiplicity. Multiplicity is the number of times that a 0 occurs in a function, meaning if it's a double root, like x squared, that means the graph would bounce at 0, right? So if the multiplicity is odd, meaning the degree of your, factor here is 1, 3, 5, 7, odd multiplicities will have an alternating pattern, meaning it'll go positive, negative, you can verify that for sure. If the multiplicity is even, that means if this is positive and this is a multiplicity of x squared, this is going to be positive also. This is going to come up again, so we'll go through it more. But if you take a look at the degrees of all of these, the multiplicity is what? It's 1. It's odd. It's an odd number. So that means it's going to alternate. So you always start on the right. This will be positive. And what that means is any value that I pick from here, let's pick 3. If I plug 3 into my original function, I'm going to get a positive answer. 3 over 3 plus 2 is positive, times 3 minus 2, which is it's positive. So that means this is going to be negative, because I'm alternating, odd multiplicity. This is positive, and this is negative. It's a lot quicker than picking numbers and plugging in, agree? But it takes practice, and you have to remember what I said, which was a lot. Okay, what do we really care about, though? As we approach from the right, we care about this one. Yes? Okay, so what we want to know is what's happening. Does the graph shoot up towards positive infinity or down towards negative infinity? If this interval gives me a positive value every single time, that means my values are going to go up to positive infinity. If this was negative, that means my answer would be negative infinity. So here, this is positive infinity. I know it was a long explanation for a teeny tiny answer, which really is a big answer, but this will help you when you do your problems, as long as you understand. Does anyone have any questions on this? We have one more problem. No? Okay. Last example. We have a piecewise function, and you are given domain restrictions, and it says that this function is x squared minus 7x plus 12 over x minus 3, but only when x is not equal to 3. Why? What happens when I plug in 3? I get a 0 on the bottom. Okay, so what they're asking us to do here is find k, meaning find this number, or basically they're saying what's the y value, okay, so that when I evaluate f of 3, I will get the same answer as I get when I evaluate the limit as x approaches 3, meaning from both sides. So if I take a look at this function, the limit as x approaches 3 of the top function, I'm actually going to factor the numerator. What's the numerator factored? That's right, x minus 3, x minus 4. So tell me what's happening at x equals 3. What's happening there? Yep, I got a hole in the function. So if I cancel this out, because remember holes are removable discontinuity, I can remove them because they cancel each other out, I now have the limit as x approaches 3 of x minus 4. Can I use direct substitution? Yeah. So what's my answer? -1. So what we're saying is, if this is now my function, okay, and I evaluate f of 3, what's f of 3? -1. And when I evaluate the limit as x approaches 3, I get -1. These are equal. What does k have to be? -1. Okay? Now, here we had our function. We had to factor and cancel out the whole, which then created an alternative or new function. Granted, this is kind of a boring function. It's a polynomial of degree 1. It's a line. But it's still a function, isn't it? Passes a vertical line test. Agree? Okay. So right here it says, with the k value assigned of -1 that we found, the value of the limit as x approaches 3 for f of x, okay, we want to show that f of x, meaning this, can be expressed as a polynomial. Right now, this is not a polynomial. When you have a rational function, it's not a polynomial. But didn't we simplify it and it then became a polynomial? What is the polynomial? A little bit louder. X minus 4 is correct. We canceled out the whole, and we got rid of the denominator, which is what made it a rational function and not a polynomial. So now, even though it's boring, it's still f of x is equal to x minus 4. Polynomial. K is assigned. It's -1. Done. Okay, does anyone have any questions? Are you sure?